But I don't understand this. Well, let me explain it to you. This first one says that if you are taking the integral of a constant function, what does the graph of a constant function look like? No. Right. Well, yeah, but be more specific. A horizontal line, right? So this is my graph right here at x equals c, and I want to find the area between A and B. Then this is just going to be one big rectangle, right? With a width of B minus A, so that's where this comes from, and a height of C. Okay? So that's why this formula says that. So if, for example, you were going to take the integral from 1 to 3 of 5, what would your answer be? I'm trying to unconfuse you. What would the integral from 1 to 3 of 5 dx be? 10. Because this would be a rectangle with a height of 5 and a width of 2. Okay? So what this is saying is you just subtract the limits of integration and multiply it by the number. Okay? All right, then the rest are fairly straightforward, and I don't know if you need to write them down besides number 1. Okay, number 2 says if you're taking the integral of two curves that have been, two functions that have been added together, you can, just add the individual, the integral of the sum is the sum of the integrals. Same thing with derivatives, right? When you took the derivative of x cubed plus 2x, it's the derivative of x cubed plus the derivative of 2x. You can do them individually, okay? Same thing here. If you have a number that you're multiplying a function by, and this one's actually very useful, you can just take that function and put it in front, do the integral of the function itself, and then multiply your answer back by that. So in other words, if you were trying to find the integral from 1 to 5 of 3x squared, what you can do with that is you can say, well, I'm just going to take the 3 out, do the integral of the simpler problem, x squared, and then in the end, multiply my answer by 3. Okay? And then number 4 is the same as number 2, but just with subtraction. If you have two functions being subtracted, you can take the integral of the individual functions and then subtract your answers, and you get the same result. Okay? So this is just a way that you can kind of break them down into easier problems. Okay? No, you're going to use a secret formula that I will reveal to you on Monday.
But it's going to make everything easy.
Correct.
What's happening tomorrow?
I'm actually going to be gone tomorrow.
So what are we doing?
Just leave you a worksheet.
Wait,
No, thanks.
or do you want an extra credit for worksheet?
I'm going to try and give you something that actually has to do with calculus.
Okay. What? Is it done? Oh, it's time. It's
All right.
time.
All right. Everybody have this?
I know. Yeah.
Okay. Shh. All right. So let's use these properties to evaluate the integral from 0 to 1 of 4 plus 3x squared dx. Okay? Waiting. So, beginning of the week, I know that was pretty rough. We spent a lot of time talking about this conceptual stuff, and there were rectangles and weird symbols in there, and what in the world is going on. We're getting more and more concrete here to where we can actually solve some problems. Okay? We're just dipping our toe in the water. We can still only do easy ones, but hopefully you're understanding a little bit about what we're doing. Enjoy calculus?
Whoa.
You mean the conceptual part? Or is it like, are you asking me, is it a
In
fight?
general.
Is it a fight every single time? Yeah, pretty much.
You never have kids that are like, whoa, now learning more today? Like, you don't have kids like that?
No, not really.
You haven't had any students
No, but that's not the key. The key is the kids that I have that are successful are the ones that ask the question, why?
You
I mean, I ask the question why all the time, but I don't.
Well, but
Yeah, when I say
you're asking
why,
why, like when I write 3x plus 2 equals 7, and then I say x equals, and you go y. I mean, like,
Understand the concept.
yeah. And so you guys, of course, have heard of the legendary Adam Big Hill, and I would put him in that category. And what made him a great athlete is that he would come in and he would not just say, just give me the formula. He wanted to understand why
that
does
made
this
them
work out.
happy.
That was part of it, yeah, because he always wanted to do his best at everything.
Yeah, he loved
He
that.
always in everything that he did, totally committed himself to that. And so sometimes he would say, how do you do that problem? And I would say, well, you can do it on the calculator, or you can use triangles. Which way do you want me to show you? And he would say both. Okay? I don't know.
He's
Anyway,
using so much calculus in his career.
Gabby, but that's the whole point. It's not about that. It's about how you approach life.
It's
You
life
approach
skills.
life by trying to tear everything down and saying it's stupid and I don't care. Why do we have to do this? And so you're
Only
choosing
calculus.
to live your life that way.
Only
No,
calculus.
English
So,
too.
yeah.
In English.
Instead of saying, I don't care, no matter what you throw at me, I'm going to try my hardest to attack that. And I'm going to assume that the reason you're asking me to do that, there's a good reason for it. Gabby, it's a fight every year, always. Okay, so we're going to break this down into 2 different pieces. Okay, so this is from 0 to 1 of 4 dx plus from 0 to 1 of 3x squared dx. Okay, so that's one of the things there that you can take them that are being added together and break it down into 2 simple pieces.
But 4 doesn't.
So that's the one that would be a.
No?
Yeah,
Right,
that
this
one
is going to
was
be a
square.
rectangle. Okay, and so the answer to this one would be 4, okay? The person that comes to mind with the why question would be Tyson Lovell. He always did that to me last year. Why is that?
What?
Yeah,
Gabby?
that's
Gabby? You had your hand raised?
Yeah,
I'm
I was
calling
gonna
you.
ask. So on the second one, even though you already split it apart, does that mean you can split it apart again?
I can't split it apart, but what I can do is
Well,
I
like
can take
with the
this
3
3 and put it in front.
Yeah.
So I'm going to say that's going to be 3 times the integral from 0 to 1 of x squared dx, okay? You all,
I don't get this. You keep going on.
you don't get what? Why?
Yeah, I got 4.
Oh, I use this rule right here. If c is a constant, I just multiply the number by those 2 things, subtract it, because what I'm saying is I want to go from 0 to 1, and my equation is y equals 4. So this is just a
You start out
rectangle
with
with a width of 1 and a height of, hold on, a width of 1 and a height of 4, and so 1 times 4 is 4. Okay, so that's what we're doing when we are answering this question right here. You're saying, what is the area underneath the curve, y equals 4 from 0 to 1? Okay? All right, and then Gabby said I can pull this 3 out to make this an easier problem. And what I started to say is, you already know the answer to this one right here.
It's 3.
We did it before in class.
Is it the equation thing?
But what was the answer?
Over 6.
So this is the parabola from 0 to 1. We did it, we wrote it in the weird thing, we took a limit, we made
Yeah.
3,000 rectangles and then added it
It's
up.
1/3.
Is 1/3, good. Okay, so this is going to be 4 plus 3 times 1/3, and so that is
5.
5. Okay, all right,
That was
okay.
What kind of a person is Taylor?
If you said Evans, like the grumbling.
I'm going to go with Colin's answer there. He is 1.
What about me?
All right, here's another little property that you can use to solve integrals sometimes. If you want to take the integral from A to C and then from C to B, why do that? Just go from A to B in the first place, right? Because if you're gonna go from A, oh, trust me, from A to C, and then from
Why
C
can't
to
just be
B,
in the middle?
you can, that is kind of weird, isn't it? Then you can just do the whole thing by going from A to B. Okay, does that make sense? All right? All right, and so for example, if you know that for some function f of x, the integral from 0 to 10 is 17. In other words, the area underneath this curve, whatever weird curve it is, from 0 to 10 equals 17. And then you also know the area from 0 to 8 is 12. We would like to figure out the area from 8 to 10.
5.
Sure, yeah, you can just subtract. Okay, yep.
Really?
And then you get 5.
It's
Yeah.
5?
Uh-huh.
That's the cool, that's the only thing that makes
Oh
sense.
my gosh, Mary.
That's like the only thing that's made sense so far.
You got it?
Yeah.
Okay, because if it's going to be 17 all the way from 0 to 10 and it's only 12 from 0 to 8, then there must be 5 left over to make a match.
Yes. Did you see that?
Sure.
Like, did you figure out?
So here's f of x,
Used to.
and here is 10, and this whole area, Taylor, is 17. Okay? Then, in a different color, the area from here to 8 is only 12. Okay? So if this whole thing is 17 and this much is 12, then what's left over there must be 5. Okay? Uh-huh.
Does it make a difference that it's 0 to 10 and 0 to 8?
Yes, if we went, hey, Pua asked a great question. She said, does it matter that we went from 0 to 10 and 0 to 8? And the answer is resoundingly yes. If we had gone from 10 to 0 instead, what would the
Would have
answer
been
be?
negative.
Negative 17.
Wait,
Okay?
I think
So that would have changed it.
I don't understand that because it's still above the.
Right, but you're going backwards this way, and so since you're going from right to left,
But
I'm
why
saying
is
that's going to be negative.
What seems like it could be.
We had negative area yesterday.
It seems
What
like
is-
it
That was
could be just like
below
a
the
displacement
x-axis,
thing.
so
Yeah,
that makes
that's what I'm
sense.
saying. It seems like that shouldn't matter. It's
But
the
it does.
same distance.
I understand.
Question.
Okay, and so when we say that the integral is the area underneath the curve, we're fudging a little bit because we are bringing negative area into play, and obviously that isn't true. Okay, and so it's conceptually the area under the curve, but literally not. Okay, yes. Okay, Kate?
No, seriously. Okay, so on the, if you're under the, like, if it's a negative one, like under the x-axis,
But it's going
and
backwards.
but it's going backwards, there's a positive.
Nice, I was hoping you were going to say that, then it would be positive.
Then you were gonna skip to game.
Yeah, well, I called it, you started laughing. See? Oh, okay, good, yeah, so those two negatives would make that be positive, okay?
It's a carbon monoxide sensor.
What is that?
Uh,
Detector?
I think it's a wireless router.
Okay.
I don't know why we have
I don't
that.
know, you're really tall
Okay.
though.
It's a
Uh,
carbon monoxide sensor.
All right, so then here are some further properties of integrals that aren't really very useful. You probably shouldn't panic and write them down or anything. But hopefully you understand that if f of x is greater than 0, in other words, if the curve is above the x-axis the whole time from a to b, then the integral is going to be positive, okay? If f of x is above g of x from a to b, then since f of x is farther from the x-axis, its area is going to be bigger than g of x's, right? Okay, pretty straightforward, all right? And then if f of x is in between two numbers m and big M, then it's going to be, the integral is going to be in between what the area would be for this and what the area would be for that, okay? That's not, don't worry about that stuff, okay? All right, so we're sort of getting integrals into the real world here a little bit, figuring them out using area formulas and coming up with real numbers for them, all right? Okay, so let's practice some of these. How many rectangles would you like to draw? Just kidding. Oh, I have one more. I can't record.
Yeah, and then you like set up your life.
You
from that.
we did it.